Students, welcome to my 7th class in nuclear physics. First, let us do a short recap of whatever we did in our last class. So, as you will remember, we were doing quantum numbers for individual nucleons. Now, students, why do we need quantum numbers, or what is the significance of quantum numbers? Let us go back to to atomic physics. So we had seen that in the atom we had a nucleus which was positively charged, and we had electrons, and the simplest atom is the hydrogen atom, where we had one electron. So we had one proton and one electron. Now when we say quantum numbers, here we talk about the electron actually. So we talk about the quantum numbers associated with these electrons, and it actually determines the state of the electron. So we have the principal quantum number n. So we have different like this: n is equal to 0, which is called the ground state, then n is equal to first excited state, the n is equal to 2. So these are the principal quantum numbers, and when an electron jumps from a higher to a lower, we get a emission spectrum, and so on. All these things. So energy is emitted in form of radiation. So these are very familiar to us. And then, but then this is not the only thing that we have. We find that again we have something called L. So we have L, which is the orbital quantum number. So with every n there is an associated L. There are a number of associated L's. So we have 0, L has got values 0, 1, 2, up to n minus 1. So accordingly, every energy level again actually has got sub energy levels like this. So if n is equal to 2, then what happens? We have L is equal to 0 and 1. So things are like this. So that means what actually looked like one energy state actually has got 3 different states associated with it, and like that. Now then again we have the orbital magnetic quantum number, which when you apply a magnetic field to the atom, then what happens, that every L again breaks up into twice L plus 1 different states. So here you see each one of this L breaks up into twice L plus 1 states, and so things becomes more and more complicated, and we get finer and finer details about the energy states of a atom. And similar is the case in case of nucleus. Although there we don't have a Coulomb potential acting on it, the field and the force is much more complicated than our well-known Coulomb interaction. But then there is also here too we have this concept of quantum number, and here we talk of quantum numbers of individual nucleons. What do we mean by individual nucleons? So let us look at this nucleus. In a nucleus we have protons and neutrons, and so as the mass number increases, we will have more and more protons and neutrons. So each of these, associated with each of this, we will have quantum numbers, and we had seen that we have the principal quantum number, which is the same as what we got in atomic physics, the orbital quantum number small l, the radial quantum number nr, the spin quantum number s, and the total quantum number j, which is the sum of l and s. So these are certain things, and then not certain things, these are certain quantum numbers, and associated with this we also have the ml associated with this l, and we have associated with s, we have ms. So these are not much different from our atomic the quantum number of an electron in the atomic case. Now then, in addition, we also learned in our last class about these quantum numbers called the isospin quantum number, the parity, which is denoted by pi, which I suppose I did not mention in the last class. So this is the parity, and then we have quantum statistics. So actually quantum statistics, I cannot assign a particular quantum number. It is much different from a quantum number, but then we will come to it while doing the nuclear models. So isospin quantum number is something that differentiates a proton and a neutron, and later on isospin quantum number is a quantum number that first arose to differentiate between, it was first designated to find to show the difference between a proton and a neutron, but later as you must be aware, there are more than 100 elementary particles, not just the proton, neutron and the electron. So all these which undergo nuclear interactions, they all have the isotopic quantum number associated with it. So parity is also a very quantum aspect which we will do later on. So these 3 points we will be doing later on. So since we are doing the general properties of the nucleus, we just introduced ourselves to these 3 topics. Now moving on, quantum properties of nuclear states. So we have nuclear energy levels, which we have already known, and then we talk about nuclear angular momentum, parity and things like that. So we have isospin statistics, and after that we go to nuclear magnetic dipole moment. Now one by one, let's look at the things. Nuclear angular momentum. What we saw in our last class is that we saw that every nucleon has a angular momentum associated with it. Now what is nuclear angular momentum is that, as we saw, if I have got a nucleus with mass number A, that means there are A numbers of nucleons, that means a certain number of protons and a certain number of neutrons. Now with each of these nucleons we can associate a orbital angular momentum, or the orbital quantum number. So you see that with the protons and the neutrons, we all associate a quantum number h cross by 2, and as a result, if I have got a large number of protons and neutrons, the angular momentum should add up. So the angular momentum, these are the quantum numbers. So angular momentum actually are multiples of h cross by 2, and in fact by using quantum mechanics we know that it is h cross L into L plus 1 the whole to the power half. So this we know from the atomic context, that this is the orbital angular momentum. So this is the orbital angular momentum. So with each and every nucleon we'll have a quantity like this, and then we'll also have a spin quantum number with each and every nucleon. So we have a neutron, and a neutron, its angular momentum, its orbital plus spin angular momentum. The first neutron, the first nucleon, suppose I call it first, then the second, and the nth, all of them, not nth, let's write as ath, because there are a number of nucleons, so they have also orbital plus spin. So the sum total, the vectorial sum of all these gives us the nuclear angular momentum, this one, the nuclear angular momentum. This is the sum total of the, so sometimes in some cases we have, suppose L1 plus S1 is equal to J1, then we have L2 plus S2 is equal to J2, which we call the LS coupling, or it might also be like this, L1, and then if I have got a large number, then the summation of Li plus Si, where I goes from 1 to A, where A is the mass number because we will have A nucleons, this is equal to I, and that is called the nuclear angular momentum, or the angular momentum of the whole nucleus. So that means nuclear angular momentum is denoted by capital I. That is one thing. But then the case is not always of LS coupling. Sometimes it is also JJ coupling, in which case we have L1 plus L2 summation. You may also write summation Li. I goes from 1 to N plus summation I goes from 1 to A Si. So this gives us equal to I. So this is obviously the JJ coupling, because this is, sorry, this is LS coupling and this is JJ coupling. I'm sorry. So because you see, this together gives us Ji, and when you sum up the J, so this is JJ coupling, so this is JJ coupling, and that is LS coupling. So these things actually are just a repetition of your atomic physics, and then so, but then here is one point that I forgot to mention. So this way actually, when I have a very heavy element, suppose uranium or something, so in that case you see the atomic number is very big, so you have A number of nucleons, so you have over 100 numbers of nucleons, so this sum should be very big. But it is found that I is never greater than 11 times of H cross by 2. Experimentally it has been found that this will never be greater than this. So that actually puzzled the scientists, and they thought why? Because you see, heavy elements means a lot of nucleons, each having their orbital and their spin angular momentum. So why this? This is because these things, these are, momentum is a vector quantity. So what happens? If one is aligned this way, the other may be aligned this way, and so they cancel the effect of each other. So as a result, this is the net, this is the only the net angular momentum, and that's why this experimental observation was explained in this manner. And it is found that in case of even A, and odd A, there is a difference between the nuclear angular momentum. So all odd even nuclei have half integral nuclear spins lying between H cross to 11 H cross by 2. And all odd nuclei will have integral nuclear spin other than 0.